It's been way too long since I've done any retrocomputing. So let's remedy that by making a very old computer do something it was never designed to. So what you're looking at here is an emulated Commodore PET 4032. It looks like this. The first version of the PET came out in 1977, making it one of the very first of the ubiquitous home microcomputers. It was extremely expensive, extremely underpowered, and made out of filing cabinets. Yes, really. It's powered by a 1 MHz 6502. This one here has 32K of RAM. It's got a disk system which is twice as powerful as the computer itself, and it was intended for programming in BASIC. So I can do like so. It's got no graphics and no color. It can display text only in one color, which is green. It does have a wide variety of graphics characters, as well as the ability to display text in lowercase. But you can't display the graphics characters and the lowercase text at the same time. You have to pick one or the other. The machine is currently set up in capital letters and graphics characters mode. However, I'm not interested in any of that. I'm interested in what happens if I reset the machine. It plays sound. This machine actually has a speaker. Here's a schematic of how the speaker works. It's really, really simple. There's a GPIO attached to one of the I/O chips. This is simply routed through a speaker, and that's it. That GPIO can be set to on or off. The way it plays tones is by oscillating the state of the speaker rapidly, producing a square wave, thus producing, sound. I can demonstrate that if I write a little program. And trying to remember what the numbers are I have to use for this. Oh yeah, 236 and 468, 204, go to 10, and I run it. You get an unpleasant buzzy sound. That's producing a fairly coarse square wave, and it's also rather irregular. I'm going to press some keys on the keyboard, and if you listen to what happens. So what's happening is when I press keys, the computer is taking time off to process the interrupts which are generated as I press the keys. This takes a varying amount of time depending how many keys are pressed, which causes the timing of the square wave loop to go all weird. If I insert some deliberate delays, like there, the pitch goes down. Unfortunately, BASIC is so slow that this approach here can't really produce sounds above maybe 50 to 100 hertz. To do better than that, we have to go to machine code. Here is a simple stub boilerplate program I wrote. This allows me to actually write machine code and deploy it onto the machine. So I assemble it using the Beeb ASM assembler. I go to my emulator and I do dload prog.prug. This loads it off an emulated disk. The program contains a little basic stub at the top that then runs the machine code that forms the rest of the program. So here's the basic stub, here's the machine code. A simple RTS. If I run it, nothing happens. So if we translate this into machine code, it looks like 236 SDA 59468 4 SDA 59468 jump entry, save, assemble, and run. It actually makes a fairly nasty buzzing sound. This is because while BASIC is too slow, machine code is way too fast. This is actually generating a supersonic frequency square wave that the PET is unable to reproduce. Also, we still have interrupts on, so pressing keys does weird things. So if I reset this, and now I put some delays in to slow it down to a reasonable speed, Let's say so we're using the X register, put 128 into it, decrement, if it's not 0, loop. And put another one there. Let's change this. Assemble. Load. Well, that is a really horrible noise. And once again, press keys. That is not what we really want to play sound. The problem is that the interrupts are messing up everything. So in fact, if we just put an SEI at the top of the program, that will disable interrupts entirely. So assemble. And we now get a nice pure sine wave tone, which we can only stop by resetting the machine. We can vary the tone by changing the length of these delay loops. So let's actually factor these out a bit. Define a routine called wait. Let's change this to 200. Loop RTS. So now we can just do JSR wait. JSR wait. Like so. And what this does is produces a lower pitch. And this is how that startup sound is produced. It simply toggles the speaker bit rapidly in various different patterns and produces those tones. But I want to do something else. And for that, first I'm going to have to explain. So a word of warning, the sketching you're about to see is going to be really bad. I am drawing a sound wave. In the real world, this is air molecules sloshing backwards and forwards. There we go, so beautiful. Computers deal with this by using a microphone to turn the motion of the air molecules into a voltage, and then they sample the voltage at a regular interval and record the voltage. They can then reproduce the analog wave by sending these samples to a DAC, which reproduces the voltage, which goes to a speaker, which reproduces the motion of the sound waves. Now, the PET hardware, while it can produce sound, it cannot reproduce particular voltages. The speaker can either be on or off. So one thing we could do is to very crudely map our analog wave to a square wave and reproduce that signal instead. Unfortunately, while this would sort of work, the resulting sound quality would be terrible because the square wave, being either on or off, cannot replicate the variable amplitude of the real sound wave. So here, for example, the amplitude is considerably lower than the square wave itself. So while it will reproduce the frequency, the shape of the resulting audio wave will be all wrong. So what I'm going to do instead is something called pulse density modulation. And here is a much better diagram drawn by somebody else. Here is our audio wave. Here is a dithered square wave that produces an approximation to the audio wave. When the amplitude is low, the square wave is mostly off. When the amplitude is high, the square wave is mostly on. When it is in between, the square wave turns on and off rapidly, thus averaging out a value that is halfway in between on and off. This is actually a well-known way of reproducing sound, and a lot of common hardware does it, but usually at much higher frequencies than our sad little Commodore PET. So going back to the code, here I have a raw sound sample. This is an array of 32-bit floats. And here I have a converter that someone else has written, which so I don't have to understand the maths, which uses a thing called a delta sigma encoder to turn that 32-bit sound wave into a bit stream, which is this. So hopefully, in order to play our sound, all we have to do is to go through this one bit at a time, setting the speaker state every 1/8000th of a second, because that's the sample rate used by this. So let's give that a try. Now, because this does need to be fairly time exact, I'm actually going to use one of the PET system timers, which is implemented by the same 6522 that is actually handling our GPIO. So the PET clock rate is 1 megahertz. Our sample rate is 8 kilohertz. Therefore, the number of ticks per sample is very simply 1 divided by the other. So we're going to use the system timer to count this many ticks, and we're going to use that as the master clock controlling the playback. So I need some boilerplate. I'll just go and do that. So I've defined a bunch of constants for easy access to the 6522's registers. So now we need to initialize the timer. The timer counts down from a particular tick value to 0, and every time it hits 0, it will generate an interrupt. So we need to program in the number of ticks, which is not that, it's that. And we're storing this into T1LL high, like so. The L here means latch. This is the storage value for the tick count. The C up here means counter. This is the value that actually counts down. And we also want to configure the timer via the ACR register, which is documented here, and it contains a bunch of settings for, how the 6522 operates. So the top 2 bits here, 7 and 6, are for timer control. We want to set it for continuous interrupts. Timer 2 is, we're not using it. The shift register, we're not using it. PB and PA, we're not using those either. So all we need to do is to set the value to 01000000, which is, 0. Okay. And it's also polite to write to the counter register, as that will set the timer running. It should be running anyway, but that's, the slightly better way to do it. So now we have a program that initializes the timer. Does it assemble? It does not. Okay. And we should make it do exactly the same thing it did last time. There we go. So, the next thing, we have our wait routine here. This just counts down until a certain number of cycles have passed. Instead, we want to change this so that it waits until the timer fires. So what we do here is we read the interrupt flag register of the 6522. This register, which is defined somewhere here, tells the computer which subsystem of the 6522 is currently signaling that something's happened. In our case, we care about timer 1 timing out. This flag will be set every time the timer value counts down below 0. So we need to check to see whether the appropriate bit 6, is set. If it's not set, just loop round and keep waiting. Once it's set, we need to tell the 6522 that we've noticed and it can reset the flag, which we do by doing one of these things. So we want to read T1C low. T1C low. There we go. And that is all we need. So up here in our sound program, we want to put a label there and change that. And so now, every time we go around the loop, it will spend 1/8000th of a second with the speaker in one state, and then 1/8000th of a second in the other state. So let's see if that works. It assembles. What does it do? Nothing. So this could actually be a good thing. This is the emulator's debugger, which we're going to use to find out what's actually going on. I use the IO command. This dumps the state of the various hardware peripherals. So here we can see the via the 6522. Here is the counter value. Here is the latch value. 1E doesn't seem right. I mean, 1 million divided by 8,000 is 125, probably. So what's it actually doing? It is spinning, waiting for the timer to fire. This is not actually counting. Okay, have I done something wrong? I had a quick look at the documentation. It looks all right. So let's stick a breakpoint at the beginning of our program. Reload it. Run it. And let's actually step through and see what actually happens. So interrupts off. 7D is the value I was expecting, 125. I was actually looking at the wrong register here. These do something else entirely. These are the timer registers. You can see it's written 7D there. That should set the other registers. And now we can see that this is counting down. Wait a minute. Why is it overwritten that value? We program the latch value to 7D00. We clear the counter. And that has, in fact, reset these two. I don't think I'm allowed to set the counter. Let me look at the documentation. Yes. Writing to the counter writes to the latches. So what I was actually trying to do was to set the latch value and then reset the timer. However, if I just write to the latch, then writing to the latch happens. If instead I write to the counter registers, then it will update the latch, and if I write to the low register, it will reset the timer. In fact, if I write to either, it will reset the timer. So I want to write to the high one last, because that causes both latches to be transferred to the counter and initiates countdown. So I just need to change this to this, and that should be all we need. Okay, step, step, step. Right, we should have initialized, there we go. Latch value of 7D, counter value of 7D, step once. This is counting down, so let's just go. And what we should have there is a 4 kilohertz tone, because this loop here is taking exactly 2 ticks per oscillation. Excellent, that is working. All right. Now we want to actually write our player. Our bit stream is in the file called sound.a2stream. So that goes there. Good, that works. Our program now has got quite a lot bigger, to very nearly 7K, most of which is the sound sample. So we want some variables in 0 page. we need a pointer to the sample currently being played. And because that sample byte contains 8 bits, and we have to latch these out one at a time, we also want to be able to store that value. Okay, initialize by doing current sample Actually, we don't need to initialize the current sample. So our loop here is going to load the current sample, mask off all but the bottom bit, convert that to either EC or AC. These are the on and off commands we need to write to PCR to change the speaker state. And send that to PCR. Next, we want to rotate the current sample right by 1. We also need a counter. This is the number of bits we've processed. So we want to process 8 bits, and then we want to advance the pointer and load the next sample. So we load that with 8. And in fact, we are going to initialize current sample. That's wrong. Sorry, that should be pointing at our data. That should be binary data. Going to load the first value and put that in current sample. So when the loop enters, we actually have valid data. So rotate right the current sample, decrement the bit counter. If it is not 0, then jump back to the top of the loop. And at the top of the loop, we actually want to do a JSR wait. Okay. So this will clock out 8 bits, and then we fall off the end of the loop here. At this point, we need to advance the pointer and reload current sample and reset bit counter. In fact, the pointer is post increment, so the pointer is always pointing at the next value. So we just want to load the next value, which we do current sample pointer, stash that in current sample, reset the bit counter, and then we want to increment our 16-bit pointer. So if we increment the low byte and the result is not 0, then we're done. If the result is 0, then we clearly want to increment the high byte. And I think that's all we need. Let's see what it does. So load the program. It's much bigger now, and run. Oh yeah, there's a breakpoint. Go. Well, that was interesting. It wasn't right, but it was interesting. Okay. Let's step through it and see what happens. So we initialize our timer. Here we're initializing the binary data. So the address is wait a minute. I see what I've done. That should be +1. That should be 0.0. So in fact, the pointer was pointing at just random garbage in memory. Okay, go. So I think it just tried to play something and failed miserably. So here, I'm clocking the bits out right to left, so the lowest bit goes first. And now I'm wondering if my converter doesn't actually work like that. So let's try clocking them out left to right. And the way we do that is we roll the sample left. In fact, we can just do that here. Roll left. The top bit goes into the carry flag. Then we roll A. That top bit then ends up in A. And now we can stash it in X and go again. The rest of it doesn't need modifying. So what will this do? That has not worked either. In fact, I think that sounded worse than it did before, so let's put that back the way it was. And we can actually simplify this code. Like so. So now I'm wondering if the converter is actually doing the right thing. Let me just go and investigate that off camera a bit, shall I? I wrote a quick program to take the bitstream output, turn it back into a sound sample. And here it is in Audacity. And if I play it, you get... which sounds familiar. And if I play back the PET version again, and go, so in fact it's working fine, it's just playing back garbage, because I told it to play back garbage. Okay, it's possible that this converter doesn't really like operating at 8 kHz. I think it may want a much higher sample rate. So let me try reconverting into 16 kHz and see if that makes a difference. I did a bit of hunting around for delta sigma converters, and I found a thing known as a second order delta sigma converter that does a better job than the first order one that this converter was using. And the results are, well, and hear for yourself. Yes, it's supposed to be the Windows 95 startup sound. But it has clearly lost something in the conversion. Now that's at 16 kilohertz. So the sample rate of 16 kilohertz, the maximum frequency that it can actually generate is 8 kilohertz. That is 1 bit on, 1 bit off. And the way these converters work is they will produce a lot of noise at that frequency. So clearly we want to get the sample rate as high as possible. However, we're running out of two things. The first is memory. We only have 32K to deal with. The other is time. This takes quite a while to do. And at 16 kilohertz, we only have, 60 cycles between samples. Luckily, the 6522 has us covered here. It's got this thing called a shift register. You can give it a byte of data and it will clock it out to a particular pin all by itself. And all you have to do is to keep reloading the register when it runs out of data. Here is the shift register documentation. Now, this is not configurable, so the output is only ever a single pin, which you can't change. Luckily, that pin is CB2, which is exactly the one we want. And in fact, this is how the PET normally does tone generation. It sets a value in the shift register, it sets a clock speed in timer 2, and it just keeps shifting out the same 8-bit bit pattern over and over again. So we should be able to use this to make a much faster and easier sample player. So I did a bit of reading up on how the shift register works, and it's a bit weird. The shift register does use timer 2, but in a peculiar mode. Timer 2 doesn't work the same way as timer 1, so it doesn't have the free running mode, but you can make it just run continuously, ignoring the latch value. Except the latch value is used by the shift register code to determine the speed at which it shifts bits. So anyway, we do this. We want to configure the shift register itself. We want to run in shift register output free running mode. So the control value is 100, which goes into these 3 bits. So we do this. We don't care about timer 1 anymore. And I think that's all we need. Our render code is now much simpler than it was. We just need the sample pointer. We don't need the bit counter. We don't need current sample, etc. So all we really need to do is... actually, let's make a few changes here. Our wait code wants to wait for the shift register empty interrupt, which is this one, bit 2. So that is a 04. So at this point, the shift register is now empty. We need to load it rapidly because the timer is still running. If we don't reload the shift register by the time the next tick comes along, then we lose a bit. So we load our sample and we write it to the shift register. So now that's done, we actually have a few cycles to spare. So what we're going to do is simply increment the sample pointer. And we don't need this anymore. And I didn't put in a via SR. So SR is E84A. Via SR. E84A. Okay. Let's see what this does. I didn't put T2 in either. So that's E848. That's interesting. Didn't this code tell me that the contents of the low order T2 latch? So where is the low order T2 latch? There isn't a register for that. Oh, of course, it will be accessed by writing to the counter register exactly the same way that timer 1 worked. So T2 control low is E848. High, which we're never going to use, is E849. So change that to that. It assembles. And does nothing. Well, I think this is T2. Yep, it is counting down. And we are currently stalled at 420. So yes, we are waiting for a interrupt. So if I put a breakpoint at 427 and go, okay, we're not getting shift register interrupts. I wonder if we need to turn those on somehow. I do know what the problem is. The problem is that the shift register only actually starts operating when you write to the shift register, but the first thing we're doing is waiting for a shift register interrupt. But we won't get a shift register interrupt because we haven't written to the shift register. So we just move the... no, let's not do that. Let's just write a arbitrary value to the shift register to kick off the process. So, and run. And nothing happens. Okay, we are waiting for the shift register. There is a setting in the PCR under CB2 control. This is the thing we were using to actually set the speaker setting, low output or high output, which is pulse output, which I think we may have to set. So let's do that. And the values we were setting down here were CC or EC. So we want 101, and CB1 control was 0. 1010, which is A. And the low nibble wants to be a C. Okay, let's try that. And we've hit our breakpoint, but that doesn't mean anything because the breakpoint has actually moved. So delete breakpoint 1. Then we'll put the new breakpoint at 431. Go. Nope, hasn't helped. Oh, for heaven's sake. So in free running mode, the interrupt is never set. That's why I'm not getting an interrupt. So this just isn't going to work. I'm going to have to do something else. Well, I could use shift out under T2 control. With this, you do get the interrupt. So you see, IFR2 is set after 8 shift pulses. The only problem is that, as far as I can tell, shifting is initialized by writing to the SR register, so that after my 8 shift pulses, there will then be a gap while I think about things, and then when I write to SR again, it will shift another 8 bits, so that you won't get seamless output without, a lot of careful cycle counting, which is annoying. But I can do something else. I can use both timers together. So we use timer 2 to control the shift register, and we use timer 1 to decide when to reload the shift register. So we set up both timers, and we want to set ACR so that timer 1 is producing continuous interrupts. So that's a 4-bit as well as the 1-bit, that's a 5. And then down here, we actually want to wait for timer 1 to roll over, which will happen every 8 ticks. At which point we reload SR. And because we're using timer 1 here, I want to clear the interrupt. Read T1C low. There we go. So what does this do? Oops, something wrong with the keyboard there. Well, that was exciting but wrong. But I think I know what's happened here. If we go down and look at the SR documentation, wherever it's got to, here we go. When shifting out, bit 7 is the first bit out. So in fact, this is sending data in the other direction than my converter app has produced it. So I'm going to have to change that. So here is the bit where it actually sets the bits. So what I actually want is to change this to a shift right by nmod bits. So VCC converter sound assemble and that has also not worked. Why is this not working? I mean, it is very clearly playing sound. It is a sample of some description. It's just not the right one. Here is the program. It's a tiny amount of machine code followed by all the sample data. Now, one possibility is that my timers here are not matched up properly. This is hopefully outputting 1 tick every ticks. I wonder if it's like 2 times. Let's change this to... I don't think this is right. I'm just going to see what happens. I heard Windows sounds there. Okay, my suspicion here is that my 2 timers are out of sync. So we're actually resetting this here. But then it's a fair number of cycles until we go here. So I think that we need to re-kick the timer with the appropriate value. So the timer is in free run mode. Where am I? Here we go. So that I can reset the timer by writing to the high counter register. So if I were to simply move this code down here, that should reset the timer. And I don't need this anymore. However, it's a little bit more complicated than that. So if we make slow ticks equals ticks times 8, so that this now becomes slow ticks, like so. We can then change this to slow ticks as well. The thing is, we write to SR. SR starts shifting. We then spend a certain number of cycles doing this and a certain number of cycles doing this. So slow ticks here, that should be an 8, is actually ticks times 8 minus a certain number of cycles. So it's a LDA constant, which is this. Immediate is 2 cycles, followed by a STA to absolute address, which is 4 cycles. So I think that's going to be ticks times 8 minus 6. Okay. So I think I can actually hear some Windows startup sound in there, but it's way noisier than it was doing it the other way. So something's not right. Let's do some single stepping and see how things work out. So here is our program, and 439 is where we is where we're actually setting the timer. So go run. The state of the timers are, this is of course free running. This is counting down from 01 dB. Step. Okay, write to SR. Write to the high byte of timer 1. Timer 1 has been reset to 01 EE. This is the shift register value, and we go around again. Unfortunately, it looks like the shift register value rolls around, and I'm not even sure it's actually shown here. I think it may be a special internal value that you're seeing. I found a different data sheet for the 6522, which actually goes into more detail about how the shift register modes work. So I think I can actually use the single shot shift register mode. Shift out under T2 control. There's a bit here that says that the shifting operation is triggered by the read or write of the shift register if the SR flag is set in the IFR. Otherwise, the first shift will occur at the next timeout of T2 after a read or write of the SR. So we do have control of what's going on there. Okay, so let's get rid of this timer 1 stuff and go back to our old code. Actually, let's just hit U for a while. Like so. We want to change this because we want to run the shift register in mode 5 rather than mode 4. So that's a 4 there. So here we are waiting for the shift register to finish shifting. Then, and this is the important bit, we want to clear the SR flag in the shift register, which is interrupt flag register cleared by read or write shift reg. But there's the other way of clearing the flags. The interrupt flag register may be read directly. Individual flag bits may be cleared by writing a 1. So we clear that bit. Now we can write to SR here, and T2 will continue to run, and after this happens, the next bit will be clocked out on schedule according to T2, rather than being synchronized to this right here. So let's try that. Deload. Prog.proof. Okay, that actually worked, but there's something wrong. I think it's running at half speed. So let's change this to ticks divided by 2. Okay, that worked. So now we're using the shift register. We can actually crank up the clock rate. So let's change this to 22050, and I'll write out my tracks resample 22050, and we'll see what it sounds like at 22.05 kilohertz. It's better. Can we go higher? Well, the critical factor is the number of cycles between here and here. So this is, and with immediate, is 2 cycles. BQ not taken is 2 cycles. LDA immediate is 2 cycles. Memory write is 4. This is 2. This is indirect comma y is 5. And this will also be 4. So 9, 11, 15, 17, 19, 21. So 1e6 divided by 21 gives us about that many hertz. So in fact, we should be able to crank this way up if we had enough RAM, which we don't. So we are currently at 18K. I think we can go to, so export at 32 kilohertz, convert, and our program is now 26K, and go. Although it would help if I'd remember to change this, 32,000. And go. It is painfully quiet, but that is because this sound here is quite quiet. So let's just normalize. Yeah, it only got a little louder. Let's just crank the volume up a fair bit. Allow clipping. Can we go a bit louder than that? I mean, it's going to sound like suck, but it's going to anyway. And go. Yeah, that didn't work very well. Let's just put that back the way it was. Yeah, I suspect that the Delta Sigma encoding really doesn't like clipping because it'll treat that as huge error values and everything goes horribly wrong. So aggressive normalization, I think, is as good as we can get. But it does actually seem to be working. Okay, let's call this the final version. Yeah, that is pretty terrible. And that funny noise is it playing all the rest of memory, because I never put in any code to stop playing. It'll wrap round. In fact, it's just played the sample again. The reason why it's so quiet is because a square wave is, of course, the maximum possible volume. So simulating a lower volume with that square wave is going to produce a lower volume. It may be possible to get higher quality, but we'd probably have to use a shorter sample because we don't have very much RAM. I bet that this loop can actually be made faster. There needs to be enough time here to reload SR before the next bit needs to be clocked out. We figured out earlier that that could be 47 kilohertz. So I reckon that we could probably play, air quotes, CD quality on air quotes sound. However, the conversion to 1-bit format is going to lose massive amounts of quality. If you're going to use Delta Sigma encoding for CD quality sound, you actually need a clock rate of, I think, 3 gigahertz, I saw somewhere. So I don't think that's gonna work. Okay, so I had to try it. I optimized the hell out of the replay loop. The critical section is now at 14 cycles. That allowed me to push the clock rate all the way up to 60 kilohertz. And as a result, it now sounds like this. And in fact, the sample is so big that it doesn't fit in memory and overwrites the screen. There you go, but the program still runs. So, listen and enjoy. So it's looping through memory in only a few seconds because the clock rate is so high. And it is super quiet because the on-off bits of the bit stream are so close together that the simulated speaker cone doesn't actually get a chance to move very far. But it does work, and it doesn't sound bad. So I think there you have it, real CD quality sound coming out of an unmodified, simulated Commodore PET, sort of. The other thing you can do, of course, is to synthesize sounds on the fly, and I do have a few ideas about doing that. But I'm not going to do it in this video. I think that's enough. I'll stick this program up somewhere, see the video description for details, if you ever want to play your own Windows 95 startup sound on a Commodore PET. And I would be very interested to know if this actually worked on a real PET. Anyway, I hope you've enjoyed this rather rambly and unstructured tour through the innards of the PET sound system and trying to make it do things it was never intended to do. It's something I've always been interested in, and I'm glad I finally got round to giving it a go. As always, I hope you enjoyed this video. Please let me know what you think in the comments, and I'll see you all next time.